What I'd like to do is to consider the special case of constant acceleration. Where a as a function of time t is just equal to a constant a. And in particular, consider the example of objects in free fall experience a constant acceleration a of t equals negative 32 feet per second squared. So this would be an example of a constant acceleration. So if I have a constant acceleration, let's also specify that we have an initial velocity of v0 and an initial position of s0. And when this happens, then I can find the velocity as a function of time t by integrating the acceleration. But because the acceleration is a constant a, therefore I just get a times t plus c. And when you plug in 0 for t, then you get c is equal to v0. So we get an equation that is going to be familiar to physics students everywhere, and that is that v of t is equal to a times t plus v0, or v0 plus at. Likewise, if I want the position, then the position is going to be the antiderivative of the velocity, and I can substitute my expression for velocity directly in here and go term at a time to get 1/2 at squared plus v0t plus a constant c. And when I substitute the initial condition of s0, then I find out that my constant c is just equal to s0. And so I get this equation. It is also familiar to students of physics. That s of t is equal to 1/2 at squared plus v0t plus the initial position. So the thing that I want to get across is that when I have a condition of constant acceleration, the velocity will always take the form of a linear equation. And when I have the condition of constant acceleration, the position will always take the form of a quadratic equation. And so to solve problems under conditions of constant acceleration, we don't have to walk through the calculus process every time because we've already done it right here in the general case. All we need to do is to find from the problem the specific information, initial position, velocity, and of course the acceleration, and we can plug in. Yes? Definitely not. That's a great question. If the acceleration is not constant, then when I pull off the antiderivative right here, I will not get a linear function. So one of the big mistakes that physics students will sometimes make is they will take a non-constant acceleration situation and they'll try to use this equation right here, and it doesn't work. So I'd like to take a look at a couple of problems where we can utilize these equations. And the first one is a ball is thrown vertically upward feet per second. Which is roughly 45 miles per hour. Be about 70 kilometers per hour. So the question now is, how high will it go? Okay. Now the first thing to recognize about this, we're also told that we can neglect air resistance. So the first thing to consider is that because we are throwing the ball into the air like this, while it is in the air, it is going to be experiencing only one force, and that is the force of gravity. It is experiencing only the force of gravity, and so because of that, we can immediately say that the acceleration is negative 32 feet per second squared. The problem doesn't tell us that explicitly, but it implies it because we are throwing this thing up into the air. And we notice that this is constant acceleration, so that our equations from the previous page can now be used. Likewise, we are told that the initial speed is 60 feet per second. And if you think about it for just a minute, you should be able to tell me what the initial position is. Where is the ball pointed as the How would you draw a picture of the ball leaving from? It would look something like this, right? You have a ball, and it's being thrown directly upwards, comes directly down. Where is it when it is thrown? On the ground. So its initial position is 0. Just like that. And so because we have previously done the calculus work of antiderivatives, we can now cut to the chase and directly plug in our information into this equation. So that S of t is equal to 1/2 of AT squared. Notice how I've got 1/2 A right there. Plus V0t plus S0. I want you to observe the mathematical form of this equation. It's a quadratic. And so it's going to have the shape of a parabola that starts at 0 and goes up to some maximum height. It comes back down to 0 again. And it is curved downwards because its second derivative is negative, concave down. So now, when we ask how high will this thing go, translate that into math form. How high will it go?
Absolute max.
The absolute max height. That's exactly right. And the absolute max height is very obviously the place where the velocity is 0. I can see that on the graph because my slope has to be 0. And I can also understand it physically because in order to be at its maximum height, the ball has to stop going up, positive velocity, and start going down, negative velocity, which means the velocity must go through 0. So the maximum will occur at the critical point where S prime of t is equal to 0. And t is therefore 60 over 32, which reduces to 15 over 8. So now, the question is, how high will it go? We didn't exactly answer that question. Instead, we found a critical time. We need to check that that critical time really is at max So let's take a look at the number line for the velocity. And when t is equal to 0, my velocity is positive 60. And when t is equal to 2, my velocity is negative 4. So you can see that we have a legitimate max because the velocity is positive until 15/8 and negative thereafter. So now, how high will it go is a matter of finding the position. Yes?
That line.
Mm-hmm. Yes, that's right. It's an S prime number line because velocity is S prime. And we're doing our sine of F prime argument. So S of 15/8 is this number, which I forget, we worked it out in the other class. Somebody want to get that number for us?
Did you say it's 22,000?
Yes. 56.25 feet. Looks like we have a question. What's that? Uh-huh. The acceleration. Yes. So the idea behind the acceleration due to gravity is that all objects are going to be accelerated at the same rate, neglecting air resistance. So if I take a relatively heavy book, I got this book here, and I take this pen right here, and I drop them, they fall together. And they fall together because they're experiencing the same acceleration.
And it's free fall line.
What's that? It's for free fall, yes. Let's consider another problem. What initial velocity must an object be thrown upward to reach the top of the Washington Monument, 550 feet? How many of you have seen the Washington Monument? How many of you have been up it? Anybody? I haven't been up it either, actually. Every time I go, it's under construction, or it's under repair, or something like that. It had to get repaired after the earthquake here. When was it? 2013? 2011? I think it was 2011. Yes, because Miss Bishop was still here. Yeah. With what initial velocity must an object be thrown upward to reach the top of the Washington Monument? Now, part of the point of this problem is no human being can do it, right? 550 feet, it's not going to happen. But we wonder, how really impossible is it? Can we just work out a little bit and get there, or is it just really impossible? So let's consider, first of all, do we have a situation with constant acceleration or not? Yes. In fact, it is a free fall situation because the object is being thrown, and as soon as it leaves the hand, gravity is the only force acting on it. So we can immediately say that our acceleration is negative 32 feet per second squared. what is our initial position?
Zero.
0, it's on the ground. What is our initial velocity? Not only do we not know, but we have to find it. So we are going to call it v0. Okay. Armed with those things now, I can say that my position, s of t, is equal to negative 1/2 of 32 t squared plus v0 t plus the initial position. Now, to understand how we should think about this, we need to draw a picture of what's going on. So here's my Washington Monument, drawing definitely not to scale. And here is my ball that I'm going to throw up, and I'm going to have it come back down, just like that. What is true about the ball at the top? Two things. Yes, the position is 550 feet, and the velocity is 0, because I am using the minimum possible initial speed so that it just barely gets to the top, and it stops right there at the top. So I can say that s prime of t, which is negative 32t plus 0, is equal to 0. And now, as a mathematician, I'm very satisfied because I have two unknowns, time and initial velocity, and I have two equations. And so I can go through and solve by either substituting or eliminating. And here, it's very easy to solve by substituting, because this equation is telling me that v0 must be equal to 32t at the top. And I can now substitute that fact in for v0 right here, so that I get s of t is equal to negative 16t squared plus 32t times t is equal to 550. And at first this looks like this is going to be a really nasty quadratic, but then it cleans up nicely, because I get negative 16t squared plus 32t squared equals 550, or positive 16t squared equals 550. And so t is equal to the square root of 550 over 16, which is equal to
14 square root and 15.
okay. But what is that decimal approximation? Nice use of 4 decimal places. I approve. Notice how long this is. Look at what happens. Somebody comes along, obviously not a human being, maybe it's Iron Man. And he comes along and phew, throws it up. 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5 1,000, 6 1,000. And just before it gets to 6, it reaches the top. And then it comes back down again. Can you imagine being able to throw it and have it hang in the air for 6 seconds before it starts coming back down? Be in the air for 12 seconds? This must be really fast. Well, we can find out how fast because we know that v0 is equal to 32t. Which is 187.6160 feet per second. For perspective, that is roughly 130 miles per hour.
So it's not too far off from the baseball pitcher.
Except the baseball pitcher is throwing horizontally instead of vertically. Yeah. when you say not too far off, it's a 30% difference from the fastest pitches, right? Yeah. Mhm.
We do have an air resistance.
And there is air resistance, that's right, and so that actually takes away, I actually calculated it once just for my own interest's sake. And basically, a baseball loses about 10% of its speed to air resistance as it goes, from the pitcher's mound to home plate, which is 90 feet. Okay, any questions on how all this goes? Okay, well then I'd like to take a look at one more problem. Makers of a certain automobile advertise that this automobile will accelerate from 15 to 50 miles per hour in high gear in 13 seconds. Now they tell us to assume constant acceleration and calculate first the acceleration in feet per second per second. Second, the distance the car travels in a given time. Now, this problem is not a particularly difficult problem. It's very much related to the ones that we have done. But if you have not been in physics, there is something that's going to trip you up. And that is that we are given speeds in miles per hour, but we are asked to find our acceleration in feet per second per second. So we have a conflict with our units. Does that make sense to everybody? You guys, you've been in chemistry, right? So you understand that units have to be compatible with each other.
A metric system.
Right, exactly, metric system. So we are going to first need to take our miles per hour, and we're going to need to turn it into feet per second. And we're going to have to do that for the 15, and we're going to have to do that for the 50. So our initial speed at the beginning of this acceleration is 15 miles per hour. Now I need to multiply by 5,280 feet per mile, and 1 hour for every 3,600 seconds. Which gives me 22 feet per second here. And then 50 miles per hour. Doing the same conversion here. Gives me 73.3333 meters. Now I've labeled this as VF for V final. And the idea is that my car is going to start right here. So here is the car. Probably not the kind of car that we were hoping for. It's a little boxy. And it's going to start here with a speed of 22, and it's going to accelerate, and when it accelerates, its speed is going to increase to 73 feet per second. And so during this time, it's going to travel a certain amount of distance. So I've labeled this information right here as V final because it is the velocity at the end of the acceleration process. Yes, how are you doing? Question? Okay, can you tell us what the question was? What your answer is?
I was asked that 1 mile equals
Yeah. It's a kind of silly English unit. The mile originally it's a Latin unit. So a mille in mille in Latin is 1,000. So a mile was 1,000 paces of a trained soldier. So a pace would be this. So 1,000 of those for a soldier would be a mile.
so we have to memorize.
It's a matter of cultural literacy. Americans know it sometimes. I will not ask you a quiz or test question. That depends upon you. All right, so how are we going to think about this? Well, here's the way we're going to think about it. Our car is experiencing a constant acceleration, and so I can use the velocity equation that we derived earlier to say that v is equal to v0 or at plus v0. Sorry, we write it with the terms reversed in physics, and so I get so used to that I just let it happen. In other words, once again, if I have a constant acceleration, my velocity must be linear. And now the information that I know is that after 13 seconds, starting at 22 feet per second, my final velocity is 73.3333 feet per second. And so doing a quick calculation, I get an acceleration of 3.9487 feet per second, which I can also write as feet per second squared. Now, to find the distance that the car travels, I need to consider my situation again. The distance that we're talking about is this distance right here. And so to find it, I can think of that as a change in the position of the car. And I can arbitrarily assign the initial position to be 0. And if I assign the initial position to be 0, then the final position is the position that I'm looking for. And so I can pull out the equation that we generated previously. S of t equals 1/2 at squared plus v0t plus s0. And the acceleration we already got was 3.9487. And the time is 13 seconds. The initial speed was 22 feet per second. And we're going to take the initial position to be 0. And now it's just a matter of computing it. and I get 600, well, to the nearest foot, it's 640 feet. Those you get,
Going up to 340.
well, yeah, I guess technically I would. There you go. Okay. How we doing? Well, I'll tell you what, we're done a little early, so I'm going to go ahead and let you get started on homework. I've already posted the assignments and you can get started on it. I'll see you tomorrow.
That's fine.